Hi everyone, I'm Dr. Syed Mustafa Safavi, a cybersecurity researcher and academic with a focus on AI, system architecture, and digital security. I'm joined by Sarah Johnson, a tech entrepreneur and strategist working across emerging technologies. In this podcast series, we combine academic insight and real-world practice to explore critical topics in tech and innovation. Whether you're a student, professional, or enthusiast, you'll gain a balanced perspective grounded in both theory and application. Make sure to subscribe, follow, and join us on this journey as we unpack the future of technology, one episode at a time.
Welcome to the show. Today we're diving into computer architecture and operating systems with a focus on processor architecture, and it's packed with details like instruction sets, pipelining, parallelism, and even processor registers.
That sounds intense. So starting off, how would you define an instruction in this context?
Well, an instruction is basically a command given to a computer. It directs the electrical signals along the appropriate circuits for processing, sort of like telling different parts of the processor what's expected. It's like a simple order that triggers a series of actions.
Right, and then we have the instruction set, which is the collection of these commands, correct?
Exactly. The instruction set defines a whole bunch of functions that a processor can perform. It differentiates computer architecture based on factors like the number of instructions, their complexity, data types, the format of the instructions, and how registers and addressing modes are used.
Yep.
It's like the vocabulary of a computer's language.
Interesting. And what are the core elements inside these instructions?
Each instruction is built from several key elements: the opcode, which specifies the task, source operands, which are like the input data, and the result operand, which tells where to store the outcome. Sometimes explicitly provided, sometimes implicitly assumed.
So the opcode is kind of like the action verb, and the operands are the nouns and objects that are acted upon.
Right, exactly. Next, we also need to consider the instruction format, which refers to the machine-specific template that outlines the length of the opcode, the number of operands, and the length of those operands. Think of it like the blueprint of how an instruction is structured.
That makes sense. Now let's talk about the classification of instructions. What are the main categories?
Good question. Instructions are generally classified into privileged instructions, which are used by the operating system to control internal CPU functions, say a halt instruction that stops the computer, and user-accessible instructions, which are available for user programs. These include things like data transfer, arithmetic operations, logical functions, and even stack instructions.
Got it. Now, an area that always sparks debate is the CISC versus RISC philosophy. What are the key differences according to the content?
The age-old debate. CISC, or complex instruction set computing, aims to improve performance by reducing the number of instructions needed per program with rich varied instructions implemented in hardware. It supports many addressing modes and sometimes uses microcode. RISC, on the other hand, keeps instructions simple with a fixed size and format so that each instruction typically executes in one clock cycle, shifting complexity to the compiler. It's like choosing between a Swiss Army knife and a simple but very sharp knife.
That's a neat analogy. But don't you think the claim that RISC simply shifts complexity to the compiler might overlook some practical hardware optimization challenges?
Well, that's a valid point. While RISC processors are designed to execute instructions within one cycle, relying heavily on optimizing compilers means that the performance gains can be limited by compiler efficiency. Still, in many modern applications, this trade-off works well because the uniformity and simplicity allow easier pipelining and parallelism.
Yeah, I see that. Speaking of pipelining, can you walk us through what pipelining actually is and why it's so crucial in these systems?
Of course. Pipelining is essentially a technique to improve performance by overlapping instruction execution, kind of like an assembly line in a factory. Instead of completing one entire instruction before starting the next, different stages of multiple instructions overlap, which reduces the overall execution time.
Right, like multitasking in a coordinated way? And what kind of problems can occur with pipelining?
Great question. Two major issues are data dependency and branching. Data dependency happens when two consecutive instructions try to access the same memory location, basically interfering with each other. Branching problems, for instance, when an instruction is a branch instruction, cause prefetched instructions to be discarded if the branch is taken.
So there are hardware and software approaches to solving these, right?
Absolutely. For data dependency, solutions include hardware-based approaches like operand forwarding and interlocks, and software approaches like delayed loads. As for branching, designers use separate pipelines, probabilistic methods, or instruction reordering, as in superscalar processing.
That's really clever. Now let's switch to registers. How are these treated in processor architectures?
Registers are small and fast storage locations within the CPU. They're crucial for holding data, instructions, and addresses for quick access. There are general-purpose registers that can be used for various functions, and special-purpose registers like the program counter, current instruction register, accumulator, memory address register, MAR, and memory data register, MDR.
Yep, exactly. The MAR and MDR operations are quite interesting. Can you briefly explain what happens during a read operation involving these registers?
Sure thing. In a read operation, the memory address is first placed into the MR. A read signal is then sent over the control bus, and the corresponding data from that memory location, say 0101, 10111, is subsequently read into the MDR. It's a neat handshake between the CPU and memory.
And what about write operations?
With write operations, the process is reversed. The data you want to write is loaded into the MDR, and the specific address, which is placed in the MAR, is used when the write signal is sent via the control bus. The memory then stores the data at that location.
Right. Now let's not forget about the flags register or the PSW. These provide status information from previous operations, don't they?
Exactly. The PSW, or program status word, holds various 1-bit flags that indicate the outcome of arithmetic operations. We have, for example, the carry flag, which is set if there's an overflow from the most significant bit, and the 0 flag, which is set when the result of an operation is 0.
And there's also the parity flag, the sign flag, the overflow flag, and even the auxiliary carry flag. Each gives us a different piece of the puzzle about what the processor just did.
Exactly so. Take the parity flag. It's set if the number of ones in the resulting bit pattern is even. The sign flag tells us if the result is negative based on the MSB, and the overflow flag is crucial in detecting errors during 2's complement arithmetic.
Yup. Switching gears slightly, how about parallelism? What benefits are we looking at there?
Parallelism refers to executing 2 or more operations simultaneously and is key to improving performance through increased throughput and speed. It's like having multiple jet engines on a plane. Each engine adds more power for concurrent processing. This can be achieved by using multiple ALUs in the CPU or even multiple processors operating concurrently.
Right, definitely. And concurrency is related to this, correct? It's the ability to run several programs or parts of a program at the same time?
Yes, absolutely. Concurrency, or being able to execute different operations at the same time, is one of the cornerstones of modern computer design. It allows systems to manage multiple tasks simultaneously, improving overall performance and responsiveness.
Finally, let's touch on processor registers again. specifically in the context of the x86 architecture. What can you tell me about that?
The x86 architecture is probably the most dominant instruction set architecture for desktops and servers. In x86, we have registers like EAX, which is a 32-bit accumulator, AX, which is the lower 16 bits of EAX, and further subdivisions with AH and AL representing the upper and lower 8 bits of AX. This hierarchical structure of registers enables both broad computations and fine-grained control during operations.
Right, got it. And these registers, they're crucial for storing temporary data, instructions for the ALU, and even addresses for executing programs. Isn't that so?
Exactly. Registers are like the high-speed workspace of the CPU. Without them, even the fastest processor would struggle with data management. They're engineered to be extremely fast so that data access isn't a bottleneck in computation.
Well, I have to say, this deep dive into instruction sets, pipelining, parallelism, and registers really gives us a solid understanding of processor architecture. Is there any final thought you'd like to leave our listeners with today?
Just that understanding these concepts, from the basic instruction to how modern CPUs optimize tasks through pipelining and parallelism, is crucial as we continue advancing technology. It's like peeling the layers on an onion, with each layer revealing more
Absolutely.
about how our hardware actually makes everything tick.
Thanks for that. It's fascinating to see how these design philosophies interplay to set the groundwork for our modern computing world.
Yup, and remember, whether it's the rich complexity of CISC or the streamlined approach of RISC, all these innovations are all about making our computers faster and more efficient. Thanks for tuning in to this rich conversation on computer architecture and operating systems.
That was a great discussion. Thanks for joining me. Until next time, keep exploring the nuts and bolts behind your CPU.